everyone, my name is Rafael, I'm an electrical engineer, and in this video I'd like to speak with you about nuclear engineering and the economics of nuclear power plants. In part 1, we're going to speak about uranium enrichment and mineralogy. The uranium found on Earth is theorized to have been created in a supernova some 6 billion years ago. Today, its radioactive decay provides the main source of heat inside of the Earth. In the Earth's crust, uranium is 500 times more abundant than gold, 40 times more abundant than silver, and about as common as tin, tungsten, and molybdenum. Uranium occurs in 4 parts per million in granite, which makes up 60% of the Earth's crust. Uraninite or pitchblende is the most common uranium mineral. The uranium-238 isotope, which is the most abundant, has 92 protons, 146 neutrons, and as you can see, it has 54 more neutrons than protons. This excess in neutrons is required to balance the nuclear forces. Without this excess in neutrons, electrostatic repulsion would win over the strong nuclear force and the atom would split apart. As all elements, uranium has isotopes on Earth. The naturally occurring isotopes of uranium are uranium-238 with concentration of 99.275%, uranium-235 with concentration of 0.72%, and uranium-234 with concentration of 0.005%. We are interested only in uranium-235. Why? Because it is the only naturally occurring element that can sustain fission chain reaction. The others don't. We are interested in uranium-235. Then, what does enrichment mean? If you have a sample of 100% uranium, they will be in this concentration of uranium-238, uranium-235, and uranium-234. To enrich uranium means to increase the concentration of uranium-235 from 0.72 that occurs naturally to 5% for nuclear power plants, or 8% or 90% for nuclear weapons. But here we are interested in nuclear power plants, and in nuclear power plants uranium is enriched for 5% of uranium-235. Uranium resources and production. The current use of uranium worldwide is approximately equal to 65,000 tons of uranium per year, and the measured resources amount to 4.7 million tons worldwide. And the countries that possess the largest resources of uranium are Australia, Canada, and Kazakhstan. The cumulative production since 1945 amounts to 2.3 million tons of uranium, and the countries that have produced the most are Canada and the United States. Uranium mining and milling. The decision as to which method of mining is going to be used depends on the nature of the ore body, safety concerns, and economic considerations. Underground mining or open pit mining may be chosen. The milling process produces a uranium oxide concentrate known as yellow cake. After dried and heated, it is packed up in 200-liter drums in concentrations of more than 80%. Uranium in power plants. Commodity markets are cyclical. Prices tend to rise and fall periodically. In certain periods, mines operate profitably. In other periods, they don't. There are 439 reactors worldwide with an installed capacity of 370 gigawatts, and they require 65,000 tons of uranium per year. In this way, power utilities can keep nuclear reactors running at high capacity and adjust supply with demand using fossil fuel power plants. Uranium fission. Uranium undergoes fission naturally, but the process is extremely sluggish. The half-life of uranium-238 is about 4.5 billion years, and the half-life of uranium-235 is about 700 million years. What does it mean? It means that if you have a sample of 100% of uranium-238, to witness half of the sample decay into other elements, you're going to need to spend 4.5 billion years. Likewise, if you have a sample of uranium-235, to witness half of the sample decay into other elements, you're going to need to spend 700 million years. See that uranium-238 decays naturally into thorium-234 by the emission of an alpha particle possessing 2 neutrons and 2 protons, and the process also releases energy. This process is very, very slow. To accelerate the process of fission, bombardment with slow-moving neutrons is necessary. The strong nuclear force, which holds neutrons and protons in the nucleus, is stronger than electrostatic repulsion only for extremely small distances. When a slow-moving neutron is absorbed by a night atom of uranium-235, it becomes a highly unstable atom of uranium-236. The nucleus will shake and rattle until it becomes elongated enough for electrostatic repulsion to win over the strong nuclear force. In this example here, the atom of uranium has split into barium, 3 neutrons, and kryptonium. The process of fission of uranium-235 produces mainly iodine, cesium, strontium, xenon, kryptonium, and barium. Uranium enrichment. The first uranium enrichment program was carried out by the United States for the production of the atomic bomb during the World War II. Atomic weapons use uranium enriched up to more than 80% of uranium-235. From the 80s, the interest shifted from atomic weapons to the production of electricity in power plants. In power plants, scientists have calculated that it is more cost-effective, more economically efficient to use uranium enriched in the range between 3% to 5% than highly enriched uranium such as those for atomic weapons. Then we come to the definition of enrichment. Enrichment is the process by which the concentration of uranium-235 is increased above its natural level of 0.7% in uranium ore to 3 to 5% in for the production of electricity or 80% for nuclear weapons. When speaking about enrichment, we oftentimes use this quantity, separative work unit, and it quantifies the effort to separate a quantity of uranium into two streams, one stream rich in uranium-235 and the other poorer in uranium-235. And the principal methods for enriching uranium are gaseous diffusion, gas centrifuge, thermal diffusion, electromagnetic separation, and laser separation. Nuclear fuel separation. The separative work unit provided by an enrichment facility is related to the amount of energy that the enrichment facility consumes. These are the principal methods for enriching uranium: gaseous diffusion and gas centrifuge. A gaseous diffusion enrichment facility consumes approximately 2.5 megawatts hour of electricity per SWU, while a gas centrifuge enrichment facility consumes approximately 50 kilowatts hour of electricity per SWU. For a light water reactor, if the reactor were to supply this electricity for the same enrichment facility that supplies it with uranium, a gaseous diffusion enrichment facility would consume approximately 4% of the electricity output of this reactor per year, while a gas centrifuge enrichment facility would consume approximately 0.1% of the electricity output of this reactor per year. Now let's talk about reactor generations. Generation 1 reactors are reactors built in the 1950s and 1960s, and their installed capacity ranged from 50 megawatts to 500 megawatts. Generation 2 reactors are reactors built in the 1970s and 1980s, and their installed capacity was in the range of 1,000 megawatts. Generation 3 reactors are reactors built in the 1990s and 2000s, and their installed capacity range from 1,200 megawatts to 1,700 megawatts. Now let's take a look at an example of construction costs. In this example, we are going to see a Generation 2 reactor. The Callaway power plant is a 1,200 megawatts Westinghouse pressurized water reactor. The cost of a nuclear steam supply system was 78 million American dollars. The cost of the turbine and the generator was 44 million American dollars. The cost of construction labor was 370 million American dollars, and the interest paid during construction was 1 billion American dollars. And the total cost of construction for this reactor was 3 billion American dollars. Financing methods. In the United States, most large power plants are financed through a variety of methods in the free enterprise economy. Among these are sale of additional stock, sale of bonds, borrowing from lending institutions. Now let's take a look at an example of annual payments. The formula for calculating annual payments is annual payment is equal to the principal borrowed times I divided by 1 minus I raised to the nth power, where I equal to 0.08 is the annual interest rate, and n equal to 30 is the number of years. Based on $2,600 per kilowatt, the amortization costs amounted to 277 million American dollars per year for a 1200 megawatts power plant. Now let's consider the operating costs. Among the operating costs are employee costs, costs with materials, supplies and equipment repair, office and facility expenses, costs of uranium mining, milling, and enrichment. Now let's see this last example of costs per kilowatt hour. Consider a nuclear power plant with net output of 1200 megawatts operating at a 90% capacity factor. We're going to multiply 1200 megawatts by 0.9 and 8,760 hours per year. And this gives 9.46 times 10 to the 9th kilowatts hour per year. The amortized capital cost will be $277 million divided by 9.46 times 10 to the 9th kilowatt hour, which gives 2.92 cents per kilowatt hour. The fixed operating costs will be $100 million divided by 9.46 times 10 to the 9th kilowatt hour, which is 1.06 cents per kilowatt hour. The fuel costs are around 0.81 cents per kilowatt hour, and the total costs amount to approximately 5 cents per kilowatt hour. So my friends, this was the video that I wanted to make. I hope you guys liked it. And I am a teacher. If you want to book a lesson with me, contact me using my WhatsApp number. Goodbye!